Assalamualaikum and good morning. Today we're going to learn about tensors. So tensors are objects which generalize vectors. So before we begin, we have to look into scalars and vectors. And as we have learned in high school, scalars essentially objects that have quantities, magnitudes, while vectors will have both magnitudes and direction. And scalars are pretty simple to describe, but vectors, one can actually look at it in two different ways. One can actually think of vector as a directed line segment. And do that. So you can think of a vector as a directed line segment, but we can also think of it as a made up of three components if it's in three-dimensional space. Okay, but these three components depends on the coordinate system of the reference frames. So one can actually change the coordinate reference frame, and you will get totally different components. So, but essentially the directed line segment is just the same thing. Only the components change according to the reference frames. And we need to know how these coordinates or the components changes under the coordinate transformation. So essentially this is how we start introducing the idea of transformation laws for vectors and tensors in general. So we begin by looking at say a general space and an n-dimensional space, for which a point in that n-dimensional space will be given by n coordinates. So one can set up a coordinate system labeled by x1 until xn. Do this. So, example here. Or one can adopt a different coordinate system and label differently for the coordinates. In this case, labeled by x1 dash until xn dash. Now, ideally, these coordinate systems will be related to each other, and how they are related are defined through functions. So for example, the dash coordinate system might be dependent on the old coordinate system of the undashed coordinate system of x1 until xn. So on the whole, each of these x1 dash, x2 dash until xn dash would be functions of x1 until xn. Now, we would like to have a shortcut for writing those down. So generally, we will try to write all this x1 dash by just x mu dash, where mu will run from 1 to n. Okay, and essentially this will be functions of the undashed coordinates. Similarly, one would think the other way around. One can actually express the undashed coordinate system by the dash coordinate system. So in other words, these will be functions of x1 dash until xn dash. Now, as we have learned in calculus, when you do a coordinate transformation, there will be a Jacobian. Okay? So you normally think in terms of a matrix, and the Jacobian that you normally do is probably the one in integrals, but here we think of it as a matrix, where the matrix is made up of the partial derivatives. So in this case, we write the partial derivative of x mu dash with respect to partial x nu, and we label this as j mu dash nu. Okay, so the labeling here follows mu dash, for example, at the top comes from mu dash over here, and nu at the bottom is due to the nu at the bottom here, even though x nu is at the top, but it's in the denominator. So when it's in the denominator, it's considered as a lower index. So that's one note. The other thing is, this is pretty artificial with respect to this x dash thing. One can actually replace this by a different coordinate system, say y mu. So it means the same thing. So in this particular case, there will be no dashes. So what are these matrix looks like? So when I write it as a matrix, I put the parentheses here. So it will be just this partial derivative of partial x1 dash, partial x1, followed by partial x1 dash, partial x2. So in other words, the index at the top, the first index that appears there, labels the row. So here is the second row, so you get the x2 dash on the numerator until the nth row. While the second index, the index at the bottom, labels the columns. So if these two functions are invertible, so one will expect this matrix to be non-singular, meaning if it's non-singular, that means the determinant is not zero, so one will be able to form the inverse. So the inverse will be essentially just the opposite of the one on top. Will be given by partial x mu, partial x nu dash. So in other words, you have the undashed coordinate in the numerator and the dash coordinate in the denominator. And it's the inverse. Simply, if you just multiply these two objects together, one actually finds that, okay, you have partial x mu, partial x nu dash, partial x nu dash, partial x rho. This is essentially like a chain rule. So this gives you partial x mu and partial x rho. And the x's, x1, x2, x3 until xn, are independent coordinates. So if they are different, if mu and rho is different, then you have 0. If they are the same, then you get 1. And this is essentially the definition of the Kronecker delta. Okay? So Kronecker delta, we index mu rho is equals to 1 when mu equals to rho, and it's equals to 0 when mu is not equal to rho. And one can actually think of this delta mu rho as being the matrix elements of the identity matrix. So you can think what this actually means. You only get 1 along the diagonal and 0 elsewhere. Similarly, if you do the reverse multiplication, you get the same thing with the Kronecker delta having the dash indices, and it is still they define the same thing. So as matrices, the two equations that I showed are just simply J inverse times J equals to the identity matrix, and J times J inverse equals the identity matrix. So once we have seen the coordinate transformation, now we can go to the mathematical objects that we normally find. First of all is the scalar, the simplest case. It's simply just a number. Okay? Remember, scalars carry only magnitudes. So in other words, one can define, say, a scalar given by phi, say in the undashed coordinate system, and then we go to the other coordinate system, the undashed, so the dash coordinate system, this phi dash, say, should be equals to phi. It's like a constant. Okay? But phi, the quantity phi itself can depend on the coordinates. It's just the value that they carry should be the same. Okay? So in other words, you can think of it here, phi dash, as a function of x1 dash, but the x1 dash are also function can be rewritten as function of x1 as a function of x1 dash. Okay, so let me illustrate this a bit more easily. So consider the case of scalar phi given by the length in Euclidean space. The length in the Euclidean space in terms of Cartesian coordinates is given by x squared plus y squared plus z squared. That's the length squared. Okay? But if you go over to a different coordinate system, in this case the polar coordinate system, these are given by r theta and phi. So x squared plus y squared plus z squared is simply just r squared. Okay, so you can see that how the scalar actually, while it's still a function of the coordinates, but they just give you the same value. So in a way, scalar is the simplest. It captures the object being a geometric object in itself. You have the magnitude in the particular case of this x squared plus y squared plus z squared, the magnitude squared. It's like a geometry is the geometric length, for example. Okay? So one should have the same idea about other objects in space. Okay. In this particular case, let's consider a vector. A vector, in this case, we consider the vector for the first case as an object with an index at the bottom. So the index at the bottom will carry the labels of x, y, z, for example, or 1, 2, 3 until n. Okay. And under coordinate transformation, we made the proposition that it actually changed under this Jacobian matrix. Okay, through the Jacobian matrix. So in this case, when you multiply the Jacobian matrix with the components, you'll get the components in the new coordinate system. So essentially, the components will change under change of coordinates. But the vector itself does not change. So that's why we need to go back to this idea of a directed line segment as a geometric object, and the components being just some quantities that depend on the coordinate reference frames. So let's take an example. Let's take back our scalar field. Okay, field is essentially that it depends on the points in the space and hence the coordinates. So if you take the gradient, which is essentially taking the scalar and take the derivative with respect to the coordinates. So that's the gradient. So you remember in the three-dimensional case, what you have is essentially del phi. So this gives you d phi dx and so on. Okay. So let's do this generally first. So you have d phi dx1, d phi dx2 until d phi dxn. So under the transformation law, one should have phi dash mu dash. The comma means actually derivative. Okay, should mention that. Okay, so this is the shorthand notation for this derivative. So with respect to the new coordinate system, the dash coordinate system will be given by that. But you can easily get this and transform it to the undashed coordinate system in this way. So it's just using a chain rule. Okay. So you have d-phi, dx nu, dx mu dash. So in other words, this is essentially the Jacobian matrix. Well, actually it's the inverse Jacobian here. And you have essentially the transformation law for the covariant vector. There is another different vector which is called contravariant vector. And for this we need to have the idea of a tangent vector. Sorry. So one normally writes a curve in this form. So you have a curve defined. So each point on the curve will have the coordinates x1, x2 until xn, but it will be related to this lambda, which is the parameter of the curve. So as lambda changes, we'll trace out a curve in the space. So in other words, you can have something like this. There's a curve, and for each point on the curve, you can try to draw the tangent vector. It's not so nice, but you know what it is. So the tangent vector is essentially, in this particular case, is just the derivative of the coordinates. Remember that the coordinates belong to the curve with respect to the parameter of the curve. And as you can see now, your single index on this vector is actually on top compared to the one before, which has index at the bottom. So one expect that the transformation law is going to be a bit different. So in this particular case, if we just write it down in the new coordinate system, the dash coordinate system, then you'll just use the chain rule again, and you'll find that, okay, this gives you the Jacobian matrix J mu dash rho, and this will be just T rho. So let's summarize that. So essentially, there are two types of vectors, a contravariant vector. So the contravariant vector will have index at the top, and there will be another kind of vector called covariant vector. And they transform according to this particular transformation law. So let's now move on to tensors. Well, remember we think of vectors in a geometric form as a directed line segment. So let's take the next object would be to think of, okay, if I can think of a vector as a directed line segment, you might want to think of something which has two vectors associated with it. So you can think of something like this, like an area for which the area is given by two vectors. So, and you can define this at all points in the space. So, and this two vectors defined on this space is essentially the tensor product of two covariant vectors, as an example. Okay. So you can have the product of this a mu b nu, and since we know how the covariant vectors transform, we can actually go to the new coordinate system, the dash coordinate system, and you'll be able to see that this tensor product between the two covariant vectors will transform in this way. It's just a multiplication of this inverse Jacobian that we had earlier. So having known how you get the tensor product between two covariant vectors to form a new object, for example, like the area that we have seen earlier, then we can generalize this to things which is not necessarily defined by product of two covariant vectors. You can think of a general object which has two indices. So in this case, you can consider the case of C mu nu. So it has two index. And this, you can think of these two index just like the components again. And it will actually depend on the reference frames. So one needs to know how this changes when you change coordinate systems. And as we have seen for the case of the tensor product between two covariant vectors, it will behave in the same way. And this is what we call a covariant tensor of rank 2. And similarly, one can do for a contravariant tensor of rank 2. But now the indices will be on top. And just like before, if you have the product of the inverse Jacobians over here will be the product of the Jacobians themselves. So one can think of this much more generally. Okay? One can even mix the index. For example, here is a different kind of tensor with one index on top and one index at the bottom, and we call this as a mixed tensor of covariant rank 1 and contravariant rank 1. And the transformation law just follows according to the indices. Okay? An example that we have seen earlier was the Kronecker delta. So the Kronecker delta will actually behave this way, and you'll see that it gives you a trivial solution. Generalizing further, you can think of any object that has some index on top and some index at the bottom, or none on top just at the bottom, or none at the bottom just on top. Okay, so you can think of it in this way. For example, then this is another tensor, much more general tensor, of which the rank over here depends on how many indices that appears. So here will be m indices on top, so that means it's contravariant rank m, and n indices at the bottom, and that's covariant rank n. And the way that they transform will be according to what we have seen earlier for the rank 2 cases. So for the rank m, which is the index on top, will have the product of m Jacobians, and for the rank covariant rank n, then they will have product of inverse Jacobian, n of them. Now we have seen how we do tensor product. You're just making combination of two, for example, two vectors, and then you get a tensor of a higher order. Or let me just make a vector is just a tensor of rank 1, whether it's covariant rank 1 or contravariant rank 1. So one can form tensor products to give you a higher order rank tensors. But you can also do the reverse. You can take two higher rank ones and form a lower rank tensor. Example over here is given by this mixed tensor for instance. Okay, you have m index on top, n index at the bottom, but let's suppose we make two of these indices to be the same. So one of them is, say, alpha on top and then alpha at the bottom. So it's given by this example here. Here's alpha here, here's alpha here. So in this case we take mu1 is alpha, new one is alpha. And remember that when you have repeated index, these are going to be summed. Okay, so these are dummy indices. And if you have remember the way we have actually talked about index notation, whatever free index on the left hand side or on the right hand side will be conserved on the left hand side. So in other words, this object for which we have actually made one of the index on top and then to be the same with another index at the bottom gives you a lower rank in one less indices on top and one less indices at the bottom. So in other words, it will be equivalent to a tensor of contravariant rank m minus 1 and covariant rank n minus 1. And we can check that by just doing, since we know how rank contravariant rank m and covariant rank n tensor transform, you can just simply check that, and you should be able to see that one of the Jacobian matrix will be multiplying with the inverse. Okay, so here's the inverse. And this becomes the Kronecker delta. Okay. So in other words, if we look at the final answer, it's simply just the transformation law for the tensor of rank 1 less from the original case. One can also do this process is called a contraction. Okay, I should mention that. So a contraction can be within tensor itself, but it can also be done by taking the product of two different tensors, in this case, and you do contraction across the different tensors. Okay, and you'll get more or less the same idea. A special case in this particular example is you take the covariant vector, for example, this is a covariant tensor of rank 1 and a contravariant tensor of rank 1, which is a contravariant vector, and make the two indices to be the same. So there's a contraction there. So this will be dummy index. So in other words, there's no free index in this object. When there's no free index in this object, it's just like a scalar. And this is sometimes called as the inner product between the vectors. And the inner product can be actually done using a Kronecker delta this way. So you multiply A mu, B nu with a Kronecker delta, delta mu nu. So delta mu nu has non-zero when mu equals to nu. So in other words, it gives you back to this particular case. And similarly for the other kind of products. So that more or less finish off this lecture. So we look into the next subject will be I think it's about how we do this in the case of more specific transformation law, which is the Lorentz transformation law. Okay, that's all. Bye.